In this video, we're going to take a look at matrix inverses, and then we're going to take a look at using matrix inverses to solve systems of equations. So, first of all, what is the inverse? Now, many matrices have inverses, not all of them, as we'll see. There's a few conditions. And the inverse is essentially a manipulated version of the original. The main property of the inverse is when it's pre-multiplied or post-multiplied by the original, we end up with the identity matrix. So if our original matrix is A, the inverse matrix is written with a power of -1 on it, which is used a lot to represent. If you remember, inverse sine looks the same. And essentially, if I pre-multiply A, so here the inverse is at the start, I end up with the identity matrix. Or if I post-multiply by the inverse. So here's the inverse after A. So here it's before A. In the second version it's after A. But either way, I end up with the identity matrix. And the main property of the identity matrix is any matrix, here I just have a random matrix called X, any matrix multiplied by the identity matrix just gives us back the original matrix. And we'll see later on how this property is very useful. I'll also explore in example 3, I'll explore this in more detail and you'll see how it is true. So in order for a matrix to have an inverse, first of all, it must be square. So a 2 by 2, 3 by 3, 4 by 4 matrix. So here we have a matrix A. And essentially there's two parts to the inverse. Again, inverse is written with the -1 as a power. So the first part looks like this. So it's simply A multiplied by D and then minus B multiplied by C, and it's 1 over, it's the reciprocal of A by D minus B by C, and that's called the determinant, because that determines whether the inverse exists or not. And then, guys, the second part, the adjusted matrix, A and D are swapped. So we swap A and D, and then we change the sign on the other two elements, B and C. They don't move. We just simply change their sign. So that's what the inverse of a matrix looks like. First of all, it must be square. There's two parts, the determinant and then the adjusted matrix. Sometimes we'll get a singular matrix, and what happens here is essentially we get the determinant. Remember the first bit, the 1 over AD minus BC. Sometimes that value ends up in a 0. And whenever we get this, 1 over 0 is an undefined value. You can't mark it on a curve or anything. It simply doesn't exist. So if you get that case, then the matrix is called a singular matrix. So there's just an example here. Here we have B. Again, there's A, D. So it goes A, B, C, D. Now, first thing we do is we adjust this matrix. So the 2 and the 6 have swapped. These two have swapped. And then we've changed the sign on B and C. So this is the adjusted matrix. And then we have the determinant. And we can see here, this gives us 12 minus 12. So that's going to give me 1 over 0. So essentially, this is my inverse. essentially the inverse doesn't exist because of this bit here. So there is no inverse, doesn't exist. So we say B is a singular matrix. So that's what it means. Is simply it can only exist in a single form as the original matrix B. It cannot exist as an inverse. So we take a look now at an example where we do have an inverse. Here's the matrix. And now we're going to find the inverse. So the first bit is simply A by D 3 by 3 minus 2 by 5. So that'll give me 1 over 9 minus 10. So that's my determinant. And now I adjust the matrix. I swap 3 and 3. Obviously it doesn't look like there's any change. And then I change the sign on B and C. So now, as I said, the bottom here goes to minus 1. It's 9 minus 10. This is what my inverse looks like. And now, guys, this is really minus 1. So I'm simply going to multiply every term inside the adjusted matrix by minus 1. So minus 1 by 3. So you simply go in and change all the signs. And this is now my inverse of the matrix A. And we'll see very shortly how we use this for solving systems of equations and stuff like that. And that's actually the next example. So I'll be doing a little bit of theory as I work my way through this as well. So the slide will look a little bit messy as we move along, but hopefully it'll make sense. So here we have a typical set of linear equations. And we're essentially asked to solve where do these 2 points meet. So both of these would be the equation of a line. And what we're looking for is this. Where is the point of intersection? And we're just going to take a look now. There's lots of ways of doing it, just exactly like this, by drawing a graph. We saw in semester 2 we could do it. In semester 1 we could do it by elimination, and in semester 2 we took a quick look at doing it by substitution. So now we're going to take a look at the same process, only using matrix inverses. So first of all, guys, we're just going to actually create a new system of matrices. And what I'm going to do is take all the coefficients here first of all. That makes my first matrix. 3, 2, 5, and 3. And the fact that they've no sign is we assume they're pluses. And now I'm going to take the x's and y's, and that makes a new matrix. So here's x and y. And if I multiply these out again, guys, I'm going to get 3x plus 2y. So I'll get back that original bit. Similarly on the bottom line, if I multiply bottom row by the xy column, 5x plus 3y. So I've essentially changed the left hand side into a system of matrices. Ooh. They're gone now. So I'll just bring up a tidier version here. Now the answer then becomes its own little system of matrices like this. So we've got 3 matrices. We have A, the first matrix. We have X, the matrix of unknowns. And then we have B, which is the matrix of our answers. And they can be written like this. Now, I'm going to tidy this up on the next slide. But what we're simply going to do, guys, we have AX is equal to B. So this will be written a bit neater. I want to get X on its own. So I want to kill the A. How I kill the A is I'm going to pre-multiply both sides by the inverse of A. And now on the left hand side, inverse of A by A gives us the identity. And on the right, the inverse is now written. And now any matrix multiplied by the identity just gives me the original matrix. We just saw this briefly. And finally, that's our answer then. So x on its own. So on the next slide, I'll just go over this. It'll look a little bit neater, but that's the essential idea. We pre-multiply both sides by the inverse of A. The idea of that is we want to kill this. We want to get rid of it, to leave x on its own. So just like I was saying, pre-multiply both sides by the inverse of A. And the inverse of A by A gives me the identity, and we're going to explore this, guys, in the last example in this video. So now these two bits here will become the identity matrix. As I said earlier then, any matrix x by the identity will always just give me back x. So the left hand side will now just look like this. So now to find x, pre-multiply B by the inverse of A. So the order in which we do things, guys, is very important. A is sitting on the outside here. So to kill it, we're going to the only thing we can do is we pre-multiply it. We can't post-multiply it because the x is in the way. So because we pre-multiply on the left, we must pre-multiply on the right. The order in which you do things, guys, this would not be the same. The order in which you multiply matrices is very important. So now we'll take a look at this translated back. In order to find x, I have to find the inverse of A and then multiply that by B, which, if you remember, B was the answers. X was the xy matrix and A was the coefficients of the equations. So go back to our example. So here we have the inverse of A, which we've already found. And now here's the answer matrix there. So now we're going to pre-multiply. We're pre-multiplying A. There's A inverse, which we found earlier. There's B. So it's going to be now just doing our multiplication. First of all, I have a 2 by 1, 2 rows, 1 column. 2 by 2 multiplied by a 2 by 1. That's a 2 by 2, so I can multiply them. And my resultant matrix is going to be a 2 by 1. So it's going to be minus 3 by minus 3, which is plus 9. And then 2 by minus 4. On the bottom line, by the first column, by B, 5 by minus 3 is minus 15. So him by him. And then second element by second element, minus 3 by minus 4 is plus 12. So this will give me then the answer matrix 1 minus 3. Remember, the matrix X looks like this when we break it down into its elements. So now, whoops, I don't know what happened there. Sorry, guys. So this is our answer. And now, so X is 1 and y is -3. So we found our answer. So we take a look at another example. Now here's my system of matrices. First thing I want to do is find the inverse of this matrix. So, sorry, I'm moving ahead. So, inverse is going to be 1 over him by him. Sorry, I'll go back to this matrix. The inverse is him by him minus him by him. So 3 by 2 is 6. Minus 1 by 2 is -1. So be very careful with the minuses there. So now we'll end up with 1 over 8. That's my determinant. So that means basically that the matrix exists, the inverse exists. Now I want to adjust the matrix, so I swap the 3 and the 2, and I change the signs on B and C. So I swap A and D, and I change the signs on B and C if we were to label these A, B, C, D. So now, like I said, this will be 1 over 8 multiplied by the adjusted matrix. And now I'm going to multiply the 1 over 8 into each term, which looks like this. Now, here guys, when we're solving these out, I'd strongly recommend you actually just leave the matrix like this, with where the main thing here is it's got a common denominator throughout the matrix. As we move through the problem, this is going to make your life easier to leave it like this. It's very tempting, and now I'm going to go down this road because it's the road most people go then, but I'd strongly advise you to pause here and jump to the next part of the problem. But a lot of people write the matrix like this. They see the 2 over 8 and they naturally, and quite rightly, simplify it down to a quarter. So we've got plus a quarter and minus a quarter here. It's just when we're finishing out the problem, we're going to have to change these back to eighths again, 1 over 8, and that's why I'm saying it makes sense to work with this matrix as the inverse. So here's the original system of matrices, and again I'm going to pre-multiply both sides by the inverse. That's going to kill the A by giving me the identity, and when I multiply the identity by x, I'm just going to end up with x. And remember guys, this matrix here is x. There's A and there's B. So taking a look, we've already worked out our inverse. I'm going to multiply the inverse by this matrix here, B. So there's my inverse, and there's the matrix B. And again guys, it's top row, here's a 2 by 2 multiplied by a 2 by 1. Can I multiply them? I can. The rows in the second matrix are equal to the columns in the first. The size of my resultant matrix is going to be a 2 by 1. So when I multiply these out guys, it's going to be top row, first element by first element, 11 over 4, plus 1/8 multiplied by 2, which is 2/8. On the bottom, minus a quarter by 11, that's minus 11 over 4, and then 3/8 by 2, which is, remember guys, just in case the fractions, when we're multiplying by 2, we can just turn the 2 into a fraction. And that's what gives me the 6 over 8. And now here guys, this is why I was saying it's good to keep the matrix with all the same denominators, because now I'm going to have to get a common denominator, multiply above and below by 2. So this will be 22 over 8, and this will be minus 22 over 8. So we've got 22 plus 2 over 8, minus 22 plus 6 over 8. We work these out, and we end up with 24 over 3 and 24 over 8 and minus 16 over 8. And that gives us our Antrim matrix then. So we can say now that x is equal to 3 and y is equal to minus 2. So that's the main kind of technique there. Finding the inverse, finding the determinant, and then using those skills to solve out the system of equations. So in an exam, I could be very specific, or in the journal, we'll say use matrix inverses to solve these equations. This is the technique I want to see. So just to be clear on that. So now, guys, we're just going to take a look. This is another common exam question, but it goes back to what we were saying on the second slide, is that when we multiply a matrix by its inverse, we get the identity. And it doesn't actually matter which order we do this. In both time cases, we get the identity. So that's exactly what's been looked for here. Show that C multiplied by it, post multiplied by its inverse, and pre-multiplied by its inverse, both give us the identity. First thing we're going to do is find the inverse of C. So my determinant, 4 by 3 minus 2 by 5. So that's 12 minus 10. I'm looking for 1 over that. Then I want to adjust my matrix, swap the 4 and the 3, and then change the signs on the 2 and the 5. Remember, don't swap the 2 and the 5, they stay in position, we just change their sign. My determinant now, guys, 12 minus 10, this is 1 over 2. And I'm going to multiply the half in again. And again, I've tidied it up, but that's just because that's what most people would do. It would make a lot of sense, as I was said, to keep these as minus 2 over 2. Strong argument for keeping that matrix. So now I know C, I know the inverse, so I'm going to post multiply C by its inverse. So it's very important, guys, to get the order right. Here's the matrix C that we were given, and here's the inverse. Now again, top row by first column. Just to go back over the basics, it's a 2 by 2 by a 2 by 2. If these numbers are the same, we can multiply them, so we can, and my resultant matrix is going to be a 2 by 2. So there's 4 elements. So we'll just work them out. So 4 by 3 over 2 is 12 over 2, and then minus 5 over 2 by 2 is minus 10 over 2. And we do the same then, top row by left hand column. Top row by right hand column was the second, was this one. That's top right, my apologies. Top left we've done. And then we go bottom row by left hand column, that's bottom left, and bottom row by right hand column. So again, you have to watch your fractions and make sure you're fairly strong with them. So now, when we tidy these up, this will give us 2 over 2. Here, minus 4 plus 4 is 0. 15 over 2 minus 15 over 2 is 0. And minus 5 plus 6 is 1. And that's our resultant matrix. And that is the identity matrix. All ones on the main diagonal and zeros everywhere else, and it's a square matrix in order. Now we look at pre-multiplying C by the inverse. So there are two different processes, but we end up with the same result. So the inverse is written first, and then the original matrix. And again, top row by left-hand column gives me the top right element, etc., etc. So just to work this one out, I always do a big rough matrix, and I'd now say 3 over 2 by 4 is 12 over 2. And then minus 1 by 5 is minus 5. Now don't try and work it out, just keep going. 3 over top row by right hand column. 3 over 2 by 2 is 6 over 2. Minus 1 by 3 is minus 3. Now, bottom row by the left hand column. Minus 5 over 2 by 4, that's minus 20 over 2. 2 by 5, that's minus 10. Sorry, plus 10. My mistake. And finally then, bottom row by right hand column, minus 5 over 2 by 2, that's minus 10 over 2. And then 2 by 3, that's plus 6. So this is how I'd always go. That'll be my next step. I don't work out each bracket, I just keep going. And now I go back and I work out each bracket. This is 6 minus 5, that gives me 1. This is 3 minus 3, gives me 0. Minus 10 plus 10 is 0. And we have minus 5 plus 6 is 1. So I'll just tidy those up. And again, we end up with the identity matrix. So that kind of nice circular end, we actually finish up pretty much where we started with inverses. And thank you for listening.